frequency response analysis. It is defined as the magnitude and phase relationship between sinusoidal input and steady state output. The definition of frequency response analysis is the phase and magnitude relationship between sinusoidal input and steady state output. Frequency response test. The test is carried out considering the system by exciting this system with a sinusoidal input, say A sin omega t, then you get the output B sin omega t plus or minus 5. So, the frequency response test is carried out by keeping the amplitude fixed and varying the omega frequency and how the magnitude and how the phase angle varies is being carried out. So, to know that how the output magnitude as well as phase angle varies with the frequency of input by keeping the amplitude fixed is the method to carry out frequency response test. There are certain domain specifications which will be helpful to analyze the system using frequency response analysis. The various frequency domain specifications which helps to analyze the given system in this frequency domain are resonant peak, resonant frequency, bandwidth, gain margin, phase margin, then gain crossover frequency, and phase crossover frequency. This many parameters are defined, are used in frequency response analysis to analyze the given system. The advantages of frequency response analysis are: number one, availability of sinusoidal signal generators, precise measurement equipment, then obtaining transfer function obtaining transfer function from frequency response curve is very easy. Then, by developing correlation between time domain and frequency domain parameters, the transient response curve can be easily obtained for higher order systems. These are the advantages of frequency response analysis. That is the reason why frequency response analysis is being more popular when compared to time domain approach. Getting a transfer function using time domain analysis or time domain plot is very laborious and difficult. But using frequency response curve, transfer function can be easily obtained, and then you can determine any of the parameters required for analyzing the stability. The various tests that are carried out to analyze the system in frequency response are Bode plot, polar plot, and Nyquist plot. All these plots are known as frequency response curves, and system stability and behavior of the system can be determined using any of these tests. It is important to know that in frequency response analysis, a system is excited by A sin omega t as an input signal, keeping this amplitude fixed, and this omega is varied for wide range of frequencies starting from 0 to infinity. How the magnitude of the system output and the phase are varied, keeping amplitude of the input system fixed by varying the frequency of the input signal. How the output, that means B, is the magnitude and phi is the phase angle, how they vary is the main motto of frequency response analysis. So, there are various plots which we are going to draw in frequency response analysis, like Bode plot, polar plot, Nyquist plot. All these curves are frequency response curves. So, any system response, say B is the magnitude here, and for frequency on x-axis, you may get a response this way. Variation in the output with respect to the frequency of input signal, say. So, I said there are some frequency domain specifications helpful to analyze the system. So, the number one is resonant peak. It is represented by MR because it is the maximum value. The definition of resonant peak is the maximum value of frequency response magnitude curve that is given In this diagram, this is MR, maximum value or peak value of the magnitude curve is known as resonant peak. So this is similar to peak overshoot in time response. Approach only is different, but here it is actually called resonant peak. It is similar to peak overshoot. The next term is resonant frequency. This is represented by omega r or Fr. If it is given in omega r, radians per second, or Fr is in cycles per second or Hz. So resonant frequency is the frequency at which the magnitude of response curve is maximum. That can be known or seen from the graph. This is the point on x-axis corresponds to resonant frequency, where the amplitude is maximum. The next term in frequency response analysis is bandwidth. This is represented by omega b, and units are similar to frequency. So this is nothing but a range of frequencies over which the signal is best way transmitted. So it is generally said this way: if the bandwidth is large, that is a good sign in frequency response. Larger bandwidth is a good indication of that system is good. So larger bandwidth in frequency domain corresponds to less rise time in time domain approach. So the meaning of rise time less in time domain approach is it is taking how much time to reach the 100% of the steady state value. So that way less rise time is a good indication in time domain, and larger bandwidth is a good indication in frequency domain. So larger bandwidth always give the improvement in transient response and also more stability. The next one is cutoff frequency. It is represented by omega c. So this is the measure of the signal that is eliminated from noise. That means when I say here this is the point corresponds to 1 by root 2 of the maximum value, is generally considered as a bandwidth. So that is the range of frequencies where you can expect the signal without noise. So cutoff frequency means it is the maximum point. Beyond that point you can find more noise. So cutoff is the limit for the best signal or best output, discriminating the noise or by eliminating the noise. So beyond cutoff, this is the point corresponds to cutoff frequency, and beyond which you will expect the signal with lot of noise. That way we define cutoff frequency. The next parameter in frequency domain specifications is gain margin. The name itself, it is very clear that what is the margin. So the amount of gain, it is defined this way: amount of gain that can be added to the system without affecting the stability. Gain margin is the amount of gain that can be still added to the system so that system goes to the verge of instability. Then it is represented by GM, gain margin, and next is phase margin. As we have seen that in frequency response analysis, our focus is on magnitude as well as phase angle. So GM or gain margin is concerned to the magnitude term, whereas phase margin is the amount of phase angle or amount of phase that can be added to the system without affecting or losing the stability. That means if you add some amount of phase angle, then system goes to the verge of instability. Beyond that, you are not expected to go. So what is that limit and what is that marginal value? We will come to know phase margin and gain margin, important terms in frequency response analysis. This phase margin is represented by PM. Now, the next term is gain crossover frequency. This is represented by GCF, and this is the frequency point on frequency response curve at which the magnitude is 0 dB. Frequency at which the magnitude or the gain is 0 dB is known as gain crossover frequency. And phase crossover frequency is represented by PCF. It is the frequency at which the phase response or phase plot crosses. It is the point at which the phase plot crosses minus 180 degree line. So these four parameters, gain margin at PCF, phase crossover frequency, and phase margin at gain crossover frequency will decide that how stable the given system is. Like relative stability, that means if you want to have more margin, you can still add to the system. You can say that it is a better system because you have a margin of adding more and more gain to the system, so that system goes to the verge of instability. So that gain margin normally it is measured at phase crossover frequency, and phase margin is measured at gain crossover frequency. All these are frequency domain specifications which will be helpful for us in analyzing the given system in frequency response approach. In order to analyze the frequency response curve, I need to have some mathematical expression. As you are aware, the transfer function is the main component that is used in time domain approach, and for standard second order system, the transfer function is nothing but ratio of Laplace transform of output to the input is given by omega n square by s square plus 2 zeta omega ns plus omega n square. This was the equation used in time domain analysis, where two important parameters can be seen here. One is zeta, that is damping ratio, and the other one is omega n, it is called undamped natural frequency. It is given in radians per second. Now, for frequency response analysis purpose, I need to have a sinusoidal transfer function. This is nothing but replace S by j omega in the transfer function, then you get sinusoidal transfer function. T of j omega is nothing but sinusoidal transfer function, that is given by C of j omega by R of j omega is equal to omega n square by j omega whole square, replacing S by j omega, plus 2 zeta omega n into j omega plus omega n square. If you simplify this, omega n square by minus omega square plus 2 j zeta omega into omega n plus omega n square. Now, this entire equation or this transfer function, you divide both numerator and denominator by omega n square. So, this becomes 1 in the numerator divided by minus omega by omega n whole square plus 2 j zeta omega by omega n plus 1. Now, I would like to have a normalized signal frequency. As you know, omega n is the system undamped natural frequency. But I am interested in frequency response analysis to see the magnitude and phase angle of the output for wide range of frequencies, omega varying from 0 to infinity. So, for that reason, I consider omega by omega n as u. This is known as normalized signal frequency I use for analysis purpose. So, this becomes 1 by, I can write minus u square plus 2 j zeta u normalized frequency plus 1. You can rewrite this as 1 by 1 minus u square plus 2 j zeta u. So if you see that this function is basically t of j omega. The sinusoidal transfer function t of j omega is given by 1 minus u square plus 2j zeta u. This can be represented in polar form, that the magnitude of t of j omega and the phase angle of the given function, where this magnitude from this is 1 by under root of 1 minus u square whole square plus 2 zeta u whole square. This is the magnitude term, and the phase angle is tan inverse the imaginary term 2 zeta u by 1 minus u square, real term. So this part is the magnitude term and this part is the phase angle term. So throughout frequency response analysis, how this magnitude and phase angle varies with u as a normalized frequency. I said normalized signal frequency, this is nothing but omega by omega n. So varying omega is nothing but varying u. That is the way this is called normalized, because with respect to the undamped natural frequency omega n, how the variation in magnitude and phase angle takes place, and with the help of that curves, after plotting, we can find out the stability parameters such as gain margin, phase margin, etc. So I need to see that how this magnitude term and phase angle term varies with the frequency. Generally we consider two extreme points, that frequency 0 and frequency infinity, and in between there we consider one value. So let us assume that, as you know that u is given by omega n, so I can consider three cases, that u is 0, u is 1, u is infinity. Now the magnitude term t of j omega, when you substitute in this magnitude t of j omega is 1 by under root of 1 minus u square whole square plus 2 zeta u whole square. So if you substitute the lower extreme, that omega or frequency u is 0, so the magnitude term will be 1. Now the phase angle t of j omega is tan inverse 2 zeta u by 1 minus u square. So the phase angle you get for 0 frequency as 0. Now the meaning of u is equal to 1 means omega equal to omega n. That indicates the value of normalized frequency is 1. For that, the magnitude is 1 by 2 zeta, some finite magnitude, and the phase angle t of j omega is minus pi by 2. Now the higher extreme, that when normalized frequency is infinity, the magnitude becomes 0 and the phase angle becomes minus 5. So this is the way the phase angle varies from 0 to minus 5 and the magnitude varies from 1 to 0. So this is the way the frequency response in terms of magnitude and phase angle variation for variation in omega or variation in normalized signal frequency can be obtained. Now if I want to get the resonant peak, bandwidth, resonant frequency, etc. in terms of zeta and omega n, similar to time domain specifications. I must take the magnitude. If I am interested to know the resonant peak, this is given by MR, the maximum value of the magnitude. This can be obtained at resonant frequency. So what I must do is, I must take the magnitude term. I must take the magnitude term 1 by under root of 1 minus u square whole square plus 2 zeta u whole square. So when is this maximum? So I must get the condition. For that, I must differentiate this d by du and then equate it to 0. So I get the condition, means the frequency at which the magnitude is maximum I can obtain from this, and I will substitute that value of frequency in the magnitude expression to get the resonant peak or the maximum value of the magnitude. So the u is here normalized signal frequency, and if I want to get the maximum value of the magnitude, I must differentiate the magnitude term with respect to normalized frequency and equate it to 0. So I can get u, that is equal to ur, because it corresponds to resonant peak, is under root of 1 minus 2 zeta square. So this is normalized value, whereas I am interested in resonant frequency, that is given by omega r by omega n. That is nothing but ur is given by 1 minus 2 zeta square. So from this I can get omega r as the frequency at which the magnitude is maximum, given by undamped natural frequency under root of 1 minus 2 zeta square. So the resonant peak now can be obtained by substituting this omega r or ur value in the magnitude expression. So I can say that the magnitude of the function maximum is nothing but mr. This is nothing but resonant peak. This is given by, I can substitute now ur or u is equal to 1 minus 2 zeta square in the expression. 1 minus 1 plus 2 zeta square whole square under root plus 2 zeta, and u equal to ur, that is replaced by 1 minus 2 zeta square to get the maximum value of that. So the maximum value of the magnitude given by mr can be now obtained by 1 by 2 zeta under root of 1 minus zeta square. So the resonant peak is independent of omega n. You can see it depends only on zeta. It is similar to the peak overshoot in time domain approach. So the phase angle term, angle of t of j omega, is given by minus tan inverse 2 zeta u divided by 1 minus u square, where u is equal to ur, that is equal to under root of 1 minus 2 zeta square needs to be substituted in this. So the phase angle or t of j omega is given by minus tan inverse under root of 1 minus 2 zeta square by zeta. This is the way you should obtain phase angle and magnitude term for normalized signal frequency. Now, if I want to draw a curve magnitude m, normally it is expressed in decibels, and the frequency on x-axis. So if you consider zeta is equal to 0.707 damping coefficient, then the curve actually you obtain like this. You will not find any peaks in the magnitude curve when zeta is considered as 0.707. But if you consider zeta less than 0.707, then the curve actually you get like this. So you can find the resonant peak. You can find the resonant peak at resonant frequency, the maximum value, when zeta is less than 0.707. This is the curve for zeta 0.707. So choosing the value of damping coefficient is also important to have the proper frequency response curve. So this is the curve straight line. You can see there is no peak in this because it is chosen zeta equal to 0.707. Similarly, if you want to have the phase angle curve with frequency, phase angle is normally expressed in degrees, and this actually has trend to go down. It starts from 0, then minus 90 and minus 180 degrees. So this is the plot, is known as phase angle versus frequency, is known as phase plot. So magnitude plot and phase plot are important to analyze the stability of the system in frequency response analysis. In order to get an expression for bandwidth in terms of zeta and undamped natural frequency, the magnitude curve, a plot between magnitude in decibels and frequency on x-axis. You get this. So the value of 0.707 corresponds to omega c, cutoff frequency, and this will be the range of frequency, that is bandwidth is defined this way. The value of the signal greater than or equal to 1 by root 2, then we say that it is a bandwidth where you can get a better signal. The response is proper during the bandwidth range. So this is the maximum value beyond which the signal gets disturbed, and that is known as cutoff frequency. So as we are interested only in bandwidth, and that magnitude of T of j omega is equal to 1 by under root of 1 minus u square whole square plus 2 zeta u whole square, you must equate this to 1 by root 2, because bandwidth corresponds to the range of frequencies greater than 1 by root 2. So now you need to have u is equal to ub corresponds to bandwidth, and this ub is equal to under root of 1 minus 2 zeta square plus again the root, you have 2 minus 4 zeta square plus 4 zeta power 4 double root. This is ub. Now ub is nothing but bandwidth frequency with respect to the undamped natural frequency is given by 1 minus 2 zeta square plus under root of 2 minus 4 zeta square plus 4 zeta power 4 double root. Now omega b is given by omega n into the whole term it depends both on zeta and omega n. This is bandwidth. Now the resonant peak you obtained in this frequency domain is 1 by 2 zeta under root of 1 minus zeta square. This you have obtained at resonant frequency omega r is equal to omega n under root 1 minus 2 zeta square. In time domain approach, we call it as a peak overshoot. MP is equal to e power minus zeta phi under root of 1 minus zeta square. This you can get at damped natural frequency omega d is equal to omega n under root of 1 minus zeta square. So these terms are frequency response terms, magnitude and frequency at which the magnitude is maximum, and these two terms corresponds to time domain approach. These two terms are corresponds to frequency domain approach. So with the help of these two, you can see now the peak overshoot or resonant peak, both are independent of omega n. They depend only on zeta. So the best value of zeta will decide the resonant peak or peak overshoot. Whether it is time domain or frequency domain, zeta is an important factor to decide whether the given peak overshoots are within the limits. Now, if I want to see the correlation between time domain and frequency domain approaches using these two expressions, if I want to compare that MR is in frequency domain on y-axis and MP also on y-axis, peak overshoot in time domain versus zeta. If I want to see the variation in their magnitudes both in time domain and frequency domain with respect to zeta, the MP, the peak overshoot, starts from 1 when zeta is 0, and it decreases, and it will be at 0.707 the value becomes 0. Whereas the resonant peak in frequency domain for zeta equal to 0, the magnitude is infinity. So when zeta is 0, the magnitude is infinity, MR, so it comes from very high value and then it decreases and it comes and stay at 0.707, that is zeta equal to 1 by root 2. Zeta value is 1 by root 2 means it is 0.707. So the correlation exists between resonant peak and peak overshoot only up to 0.707. So beyond that zeta, correlation will break down because the oscillations in time domain will be 0 beyond zeta 0.707. So this is MR versus zeta. You can see here up to this point the correlation between this and this will exist. Means for certain zeta, for certain value of zeta here x, there will be peak overshoot. This is MP versus zeta. So for certain value of zeta you have some peak overshoot, correspondingly you have some value of resonant peak. That way I can correlate. If peak overshoot is x, then resonant peak may be some value multiplied by x, so that the relation I can compare in time domain for that zeta, this is peak overshoot, then in frequency domain for the same zeta, what is MR. This comparison I can do only up to zeta equal to 0.707. Remember that correlation breaks after zeta equal to greater than 0.707. So the correlation terms between frequency domain and then time domain So as I said, MR is the resonant peak that is given by 1 by 2 zeta under root of 1 minus zeta square, whereas peak overshoot in time domain is e power minus zeta phi under root of 1 minus zeta square. So it has got some relation that was explained with the help of graph. And the omega r, the resonant frequency here, is equal to omega n under root of 1 minus 2 zeta square. And this is omega d, this is equal to omega n under root of 1 minus zeta square. Relation exists between frequency in frequency domain and damped natural frequency in time domain. Similarly, the bandwidth is the term in frequency domain. It has got some relation with rise time. So the larger bandwidth corresponds to less rise time, as rise time expression Tr is equal to pi minus theta by omega d. So as you know that the bandwidth expression omega b is equal to omega n into under root of 1 minus 2 zeta square plus so on. So this omega b increases with omega n. When omega n increases, omega b also increases. So I say that omega n is large, bandwidth is large. So when you see in the time domain specifications pi minus theta by omega n under root of 1 minus zeta square. So for larger omega n, if omega n is large, the rise time is less. So in the sense that larger bandwidth is a good indication in frequency domain is same as less rise time. Means time required for the response to reach the 100% steady state value in less time is a good sign. So less rise time is a good sign to say that system is having better response. Similarly, the larger bandwidth is same in frequency response analysis. So that way low bandwidth is bad. Low bandwidth means it is bad, and here you will have larger rise time. So this way comparison can be done between frequency domain and time domain approaches to analyze the same system.